AI requires massive amounts of power, and America's grid is running out of time.
We typically imagine artificial intelligence as invisible code living in the cloud. In reality, it is a massive industrial process that consumes raw electricity at a scale that challenges existing infrastructure. These statements from Sam Altman, Elon Musk, and Jensen Huang reflect a shift in focus for the industry. The primary concern for AI's leadership is now the capacity of national power grids. This tree map chart shows the current state of the global race, with the United States holding a commanding 74.5% share of publicly identifiable AI GPU clusters. This lead is built on an ecosystem of hyperscalers, investing hundreds of billions into cutting-edge hardware. The U.S. government maintains this advantage through aggressive export controls, which block China's access to the most advanced American-designed chips. This 3D diagram shows how generative AI has integrated data centers into a nation's strategic infrastructure. Training massive models requires trillions of simultaneous calculations, pulling power at the gigawatt scale, an amount of energy comparable to that of a mid-sized city. This diagram illustrates the physical bottleneck. An immense volume of capital and data is currently crashing into the narrow constraint of U.S. grid capacity. The aging American grid was never designed to deliver the power of a nuclear station to a single computing facility. Grid constraints have created multi-year connection backlogs and local opposition due to rising residential electricity prices. Some firms are now proposing off-grid generators or even space-based data centers to circumvent terrestrial limits. America's AI progress now faces a physical limit, the amount of electricity available from the wall. This line graph shows electricity generation since 1985. Around 2005, China's trajectory diverged sharply as the state scaled its industrial power infrastructure ahead of actual demand. China's grid capacity is now more than double the United States, with hundreds of gigawatts added annually. This has created an asymmetric race. China has virtually limitless, cheap energy, but lacks advanced chips. The U.S. has advanced hardware, but lacks the power capacity to utilize it at scale. China's strategy to bypass U.S. blockades is highlighted in this process diagram. They rely on domestic foundries to produce less efficient 7-nanometer chips. To match American performance, China aggressively stacks thousands of these suboptimal chips together, a brute force approach consuming massive amounts of electricity. This energy drain is viable in China because of state-subsidized power, costing roughly 3 cents per kilowatt-hour, half the rate paid by many American facilities. Centralized planning also means effectively zero public opposition to these massive power draws. This is visible at the Yanggao data center, built on a former pig farm specifically to access cheap wind, solar, and coal power. However, as the catchbox details, almost none of the actual silicon at the site is currently capable of intense AI training. To solve this, China is connecting Western renewable power sources directly to Eastern technology hubs. The goal is a unified nationwide computing pool by 2028. China is trading microchip efficiency for its most abundant asset, raw electricity. Artificial general intelligence will require exponentially more power than today's models. This AI layer cake diagram shows the hierarchy of needs for AGI. At this scale, energy is the foundation, the single point of failure for every software algorithm built on top of it. Because the power requirements are so high, the total cost of intelligence will eventually match the raw cost of the electricity used to produce it. This geopolitical balance sheet summarizes the two positions. The U.S. holds a hardware monopoly, but faces an aging grid. China is hardware constrained, but possesses double the U.S. grid capacity. The strategic question for the United States is whether it can increase chip efficiency fast enough to overcome its grid limitations. The question for China is whether it can manufacture enough legacy silicon to brute force its way to AGI using cheap, abundant power. American silicon won the short-term AI race, but the Electron gap is beginning to neutralize the silicon gap. The victor of the long-term race for AGI will be whichever nation solves its physical bottleneck first.